Hello everyone and welcome to a new lecture on discrete mathematics. So far, we studied several important topics in discrete mathematics which are very important for computer science and artificial intelligence students. The next two topics that we're gonna talk, and I believe they are very important for you, are induction and recursion. Why do we need induction? If you remember, we tried already to prove some mathematical statements. Induction can help us for proof. So very simple, we have two steps. In the first step, we try to prove it for the initial term, and then we go for the next term and we prove if it's okay for k, then the k plus 1 also is applicable. The next topic that we will discuss is recursion. We already learned about sets. Sets also can be defined by listing some of their elements and giving rules. So instead of like having all elements, we can define some closed form and do that. So recursive definition is used to define some sets. We start with mathematical induction. Mathematical induction for the first time was proposed by a Persian mathematician whose name was Al-Khariji. Many mathematical statements assert that a property is true for all positive integers, which we already know it as closed form. So in general, mathematical induction can be used for proof of statements that assert Pn is true for all integers of n, where Pn is a propositional function. What we can prove using induction, here are some examples of mathematical statements that we can prove using mathematical induction. For example, we want to prove that n factorial is less than or equal to the n to the n, or n to the n minus n is divisible by 3. Or we can say a set of n elements has to the n subsets. Or we can say the sum of the first n positive integer is n multiply n plus 1 divided by 2. So using mathematical induction, we can prove such statements. For intuition and better understanding the concept of mathematical induction, ladder is a good example. Suppose we have an infinite ladder like this. So we can reach the first rung of the ladder. For example, if you want to go, we need to go to the first rung of the ladder. If we can reach a particular rung of the ladder, then we can reach to the next. So from 1, we can go to 2. From 2, we can go to 3. From 3, we can go. And up to here, for example, any k is a positive integer, any one will lead us to the k plus 1. By reaching the first rung of the ladder, we can reach the second one, third one, fourth one. So this is how we work in mathematical induction. We use mathematical induction to prove Pn is true for n, where Pn is a propositional logic. And mathematical is used and applicable by following two steps. The first step is called as basic step, and the second step is called as inductive step. So what we do in the first step, we consider some like b, right? And b, for example, can be 1, and we call this one as the, for example, initial term. Right? First, we prove that this mathematical statement is true for P1. P1 can be, for example, 0, can be 2, or can be anything. Then, if it's true, we move to the second step, which is inductive step, and we show that for all positive integers like k, if pk is true, then pk plus 1 is also true. We can say pk implies pk plus 1. That's all. Two steps. P1 is true, this one. If these two conditions satisfied, then we succeed to prove a mathematical statement using mathematical induction. So mathematical induction can be expressed as the rule of inference. As I said to you, we have two conditions, right? The first condition is here, P1, and the second condition is this one. For all k, pk implies pk plus 1. If these two conditions are okay, then we can say that for all n, Pn holds. Like the 1 is not mandatory to be 1. It can be 0, it can be 2, or it can be any integer point like b. Here we want to check whether mathematical inductions are valid or not. In order to check the validity of mathematical induction, we should think about well-ordering property. What is the meaning of well-ordering property? It says that every non-empty subset of a set of positive integer has a least element. This is the point, a least element. So we want to prove this one using contradiction. So you already know contradiction. We suppose that there is at least one positive integer where Pn is false. We go and somewhere we come to conclusion that this is false. Then the set of, for example, S positive integer for which Pn is false is non-empty. Then, by the definition of well-ordering property, we conclude that S has a least number, and we say that M in S is the least number. We know that M cannot be 1 because P1 holds. So, M is not equal to 1. Since M is positive and also M is greater than 1, M minus 1 should be also positive. So, M minus 1 is less than M and it's not in S. So Pm minus 1 must be true. But since the conditional of the inductive statement, which was Pk implies Pk plus 1 for every positive integer for k whole, Pm also must be true. But this is the contradiction to here that we say is false. That's why we can say that mathematical induction is valid. A summary of mathematical induction that we discussed so far, we consider an infinite sequence of dominoes. I think you already played dominoes or you saw dominoes. So how dominoes work? They put these blocks in some specified distance to each other, and if you knock over one of them, then it will go to the end. So you see that it's a good intuition example for mathematical induction. This will be Pn. And if this knock over, the second one next knock over. If this knock over, the next one knock over, right? So this is what we discussed in here. So if we consider Pn as the nth domino knocked over, we know that the first domino is knocked over. It means P1 is true. So we also know that if we knocked over kth domino, then k plus 1 also will be knocked over. It means Pk implies Pk plus 1, right? And here it goes. So dominoes are a good example of mathematical induction. Now let's see some examples of mathematical induction. The first one is summation formula, and we want to see how we can prove it using two steps of mathematical induction. We want to show that if n is a positive integer, then sum of the first integer is equal to n multiply n plus 1 divided by 2. So based on the definition of mathematical induction, we need to follow two steps. The first one is called as basic step, and we show that P1 is true. And in the second one, which is inductive step, we prove that if Pk is true, then Pk plus 1 is also true. So when we say n equals 1, this means only we consider this one, and from this one, we instead of n is equal to 1, right? So 1 multiply 1 plus 1 divided by 2. That's why the first one is okay. The second step is inductive step. For the inductive hypothesis, we assume that Pk holds for any positive integer, then we go for k plus 1, right? So here we had n plus 1 divided by 2. Instead of n, we go for k, right? This is for Pk. Okay, then you can see that it's okay. In the second step, we go for Pk plus 1, right? So then 1, 2, 3 plus k plus 1. This is the next number to this one, right? And simply again here, k plus 1, right? Then with a very simple mathematical, you can do like this. K plus 1 plus 1. This will be 2, this will be 1 divided by 2. And you can see the format based on that one we had already is okay. So it says Pk plus 1 is true under the assumption of Pk. And this completes the inductive step. Here is the example of conjecture with mathematical induction. Let me have a conjecture. The addition of n odd integer is equal to n to the 2. It means 1 is odd, 3 is odd, 5 is odd, plus up to 2n minus 1. This is the simple definition of any odd number. And we want to prove that it's equal to n to the 2. So if you want to have some examples, for example, 1 plus 3 is 4, and 4 is equal to the 2. 1 plus 3 plus 5 is equal to 9, which is 3 to the 2. 1 plus 3 plus 5 plus 7 is 16, which is equal to 4 to the 2. 1 plus 3 plus 5 plus 7 plus 9 is 25, which is equal to 5 to the 2. So the closed form, this closed form is correct. We need to go and prove it. So we want to prove that 1 plus 3 plus 5 plus something plus 2n minus 1 is equal to n to the 2. We need to follow two steps, basic step and inductive step. In the basic step, if n is equal to 1, then, so 1 and 1 to the 2. 1 is here, 1 to the 2, and 1 is equal to 1. It's correct. Then we move to the second step, which is inductive step. To complete the inductive step, we must show that pk, if pk is true, then pk plus 1 is also true. To do this, we first assume pk. That's why we go for this one. Instead of n we have k, 1 plus 3 plus 5 plus 2. Instead of n we have k, instead, then you can see it's okay. Then we go for k plus 1. So this is pk and this is pk plus 1. Again, instead of k we have k plus 1. Instead of k we have k plus 1. Then, by simply mathematical calculation, you can come with this one, 2k plus 1 minus 1. So it will be 2k, 2, and this one. Then you can come with this one. And finally, you come with k2 plus 2k plus 1, and this one is k2 plus 2k plus 1, which is simply k plus 1 to the 2, and you can see that this is correct. So we find the first step and second step. That's why this is proved. We want to use mathematical induction to prove the geometric progression, and in here our initial term is a and common ratio is r. You already know geometric progression, and in geometric progression we say sum of ar to the j from 0 to n is equal to a plus ar squared plus up to ar to the n, which is equal to ar n plus 1 minus a divided by r minus a, and r should not be 1. So the first step is basic step, and we should go for, because j is 0, we go for p0. So very simple. Instead of n, we will have 0. So this one should be 1. So we remove this one, ar minus a. And if we do factorization here, we will have ar minus 1 divided by r minus 1. These two go and 8. So you can see that the first one is okay. So the next one is we want to go for inductive step. Remember that we're going for geometric progression. What was geometric progression? We say sum of arj, if j is equal to 0 to n, is equal to ar0 plus ar1 plus ar2 plus up to arn, which is equal to arn plus 1 minus a divided by r minus 1. So in here, we go for pk and then pk plus 1. Again, instead of n, we have r plus 1, right? Then we will go for this one. Then just we assume k plus 1, right? So very simple, k plus 1 is here, and very simple, you can calculate this one. Then we try to complete the inductive step. So we add some ar k plus 1 to both sides, right? Because ar k plus 1 is to the next of that one. By rewriting the equation, we will have this ar k plus 1 minus a divided by r minus a plus ar k plus 1. And again, if you do simple mathematics, if you give this common divisor here, then you will have this one, and this one multiply this one, you will have this one. Then by simplification, you will come to this one. And by combining these two equations, we will come with this one, which is ark plus 2 minus 2 divided by r. And this shows that pk implies pk plus 1, right? So very simple mathematical calculation, we can prove these two. We also can prove inequalities using mathematical induction. So we want to prove that n is less than 2 to the n, right? Again, we say that Pn is the proposition that n is less than 2 to the n. Then here we go for the basic step P1, and we say that 1 is less than 2 to the 1 and 1 is less than 2. Then in inductive step, we assume that pk holds. So k is less than 2 to the k for n to the k. Then k is less than 2 to the k is k plus 1 and k plus 1, right? K plus 1 is less than 2 to the k plus 1 less than or equal to 2 to the k plus 2 to the k, right? It means we move this one here, and 2 multiplied 2 to the k is equal to 2 to the k, which is correct. How many multiplication will be carried out by this pseudocode? So if we say c is 0, then we have two loops here. We call this one as outer loop, and we call this one as inner loop. As you can see, the range is 10, the range is 5. The first one is executed 10 times, and for each time of 10, we will have execution of this one for 5 times. So we can say 50 times. But if we change it a little bit, in here you can see that for I in range, the range of outer loop is 10. The range of this one is not 5. When I is equal to 1, this is 1. For 1, this repeats 1 time. Second time, this one repeats 2 times. Third time, 3 times. So you can see here 1, 2, 3, 4, 5. So you can see. Okay, here we go. In the next example, we want to prove that f1 plus f2 plus f3 up to fn is equal to fn plus 2 minus 1 if n is greater or equal to 2. It means 0 and 1 are not applicable, right? We should start with, you can say our b is 2. So we go for 2. If 2, it means we need to consider 2 of them. And instead of here, we will have 2 plus 2, f4 minus 1. This is for the basic step, right? f1 plus f2 is equal to 1 plus 1 is equal to 2. And f4 minus 1 is 3 minus 1 equals to 2. Suppose that f1 plus f2 plus f3 up to fk and fk plus 1 is equal to fk plus 2 minus 1 plus fk, right? We simply added these two parts. Then we can rewrite it as fk plus 1, this part, plus fk plus 2 minus 1, this one. And by simple summation, we will have fk plus 3 minus 1, which is correct. Another example here, we want to prove that 9 divides 10 to the n minus 1. So we go, and it gave us that we start from 0, initially 0. When n is equal to 0, 10 to the 0 minus 1 is 0, right? And we know that 9 divides 0. Based on the definition that already we had, we said, for example, a divides b, it means b is equal to ac, it means 0 can be equal to 0 not multiply 9. Suppose the statements hold for all values n up to some k. We need to show that if it's okay for k, then it's okay also for k plus 1. This is the inductive. Because n divides 10 to the k minus 1, we know that 10 to the k minus 1 is equal to something 9, some x, right? We said consider x belongs to z. Then if we multiply both sides by 10, then we will have this one. By multiplying both sides by 10, we can rewrite this one as this, and which is equal to 10 to the k minus 1, 9 multiply 10x plus 9, which is equal to this one and this. And you can see that this also holds, and this completes our induction, and proof is completed. Another example, if n is greater than 1, then 1 multiply 2, 2 multiply 3, 3 multiply 4, n multiply n plus 1, and summation of all is equal to n multiply n plus 1 multiply n plus 2 divided by 3. So we start from 1, the basics. 1 means we consider only this one. And this is here, 1 multiply 2 is equal to 2. And if we put 1 here, 1, this 1 plus 1 is 2, 1 plus 2 is 3 divided by 3, which is 6 divided by 3 is 2. The first condition is okay. Then we assume n equals k in the inductive step. Instead of n, we will have k. Then we say that if pk true, then pk plus 1 should be true. Okay. So what we are going to do, we want to do that 1 multiply 2, 2 multiply 3, 3 multiply 4, k multiply k plus 1, and k plus 1, this is the new term. K plus 1 multiply k plus 1 plus 1, right? So it means we consider n equals k plus 1. The left hand side of the equation, this one, we will write like this. So up to here, this part, we will write like this, and this is the new term that we have. Just we separated the k numbers and k plus 1 numbers. We know that for the first k number here, by our assumption, we found that k, this one, right? So instead of 1 to k, we will put this one. And this is our new term that we will have here. So for this summation of fractions, we need to find the common denominator. What is that? 3, right? It will be something like this. And if you do a simple summation of two fractions, you will come with something like this. And this says our proof is correct. If we have a sequence and its term is 5 times of the previous one minus 1. It means 5, if n is equal to 1, 5 of 1 minus 1 is 4. Then 5 of 2 minus 1 is 9. 5 of 3 minus 1 up to here. Then sum of this sequence is this one. We want to prove using mathematical induction. So n is equal to 1, simply n is equal to 1, 1. 5 multiply 1 plus 3 divided by 2, which is 4, and this is correct. We suppose it's applicable for k, then we try to find out k plus 1. You can say this one was p1, pk, pk plus 1. So we go, instead of n, we have k. Then for k plus 1, we add a new term. This is for k plus 1. And instead of n, we will have k plus 1. Then, by adding 5k plus 4, by adding this to the two parts, to the both part, we will have this one. Then, here, we need again to find a common denominator, which is 2. And by simply summation, you will come with this one. And by simplification, you will come to this, which gives that this is true. Although every problem has its own characteristics, mathematical induction proofs are very straightforward. So if we follow some guidelines, then simply we can prove them. Here are some instructions for mathematical induction proof. First of all, we express the statement that is going to be proved. For example, this is what we are going to prove for n greater than b. And you remember, this is our initial, and this is what we are going to prove for some b. Right? Then we write basic step and we show that for PB is true. We take care as the first step. Then we go for inductive step. We here state and clearly identify the inductive hypothesis. We assume that PK is true if K is greater than or equal to B. Then we state what needs to be proved under this assumption, which is pk plus 1, right? This is our hypothesis. We try to prove this one, and we make sure that our proof is valid for all k, where k is greater than or equal to our initial term. And we take care that the proof works for small values. And we clearly identify the conclusion, and we come up with the comparison of what we found, and finally, if it's true, we can say that our proof is completed. A strong induction is an improved version of induction. Also, it is called as second principle of mathematical induction. Also, it's called as complete induction. To prove that Pn is true for all positive integers like n, we follow two steps. The first step is like what we have already. We go for the initial term and we check it. Then we show a conditional statement. In the previous or in traditional induction, we say if pk is true by assumption, then pk plus 1 must be true. In here, we say that if p1 and p2 and p3 and p4 up to pk correct, then pk plus 1 is also correct. Right? This is strong induction. So a strong induction tells us that we can reach all rounds if we can reach the first round. And for every k, if we can reach the k, then we go to the next. Right? P1 and P2 and P3. It means we can come to pk plus 1 if all of the previous steps have been completely done. For example, suppose we can reach the first and second round of the ladder, and we know that if we can reach a round, then we can reach 2 rounds higher. It means 1 round which lead us to 2 rounds. We want to prove that we can reach every round. Using strong induction, first we should go to the first round. Then, the inductive hypothesis is that we can reach to the k round for any k greater than or equal to 2. We can reach the k plus 1 round since we can reach the k minus 1 round by the inductive hypothesis. So we can reach all rounds. So there may be one question that which form of induction should be used. We can always use strong induction instead of mathematical induction, but there is no reason to use if it is simpler to use mathematical induction. In fact, the principles of mathematical induction, strong induction, and well-ordering property all are almost equivalent. Sometimes it is clear how to proceed using one of 3 methods, but not the other 2. For example, we want to show that if n is integer greater than 1, then n can be written as the product of primes. We already had this example. So we consider that Pn is a proposition that n can be rewritten as the product of primes. So we go for the first step and we say 2, because 2 is the first prime, right? So P2 is okay, and by the definition we have greater than 1, so we start with 2, and 2 itself is a prime, so it's okay. Then for the inductive step, we say that for like Pj is true for all integer is, for example, j is between k and 2. Right? And we want to show that pk plus 1 must be true under this assumption. So 2 cases need to be considered. If k plus 1 is prime, then pk plus 1 is true. Otherwise, k plus 1 is composite. and can be rewritten based on the previous lectures, can be written as the product of two positive integers like a and b, and we can say a is between 2 and b is less than k plus 1. By the induction hypothesis, a and b can be written as the product of primes, and therefore k plus 1, which is here, can be also rewritten as the product of prime numbers. So it has been shown that every integer greater than 1 can be rewritten as the product of, because we suppose that these two can be rewritten, and then k plus 1 also can be. Okay, the next topic is recursive or recursively defined function or inductive definition. I think you already know this one. It means we have a function. This is a function. And inside the function, we call itself recursive. So in here, we have two steps. Basic step, specify the value of the function at 0. And the next one, we give a rule for finding rule or closed form that we have already. Finding the integer from the value at this moment. So a function like fn is the same as the sequences like, for example, a0, a1, up to something, where ai here is, for example, you can say fi. It's a kind of mapping or closed form that we already have. Suppose f is defined as f0, the basic is 0 and it's 3. The next one, fn plus 1 is 2 times of fn plus 3. So very simple, how we can find it? Initially, we have 0, so f0 is equal to 3. Go for 1. f1 is equal to 2 times f0, because this, when we say this is the next, then this is the previous one. So if it was fn, we can say fn minus 1. When we say fn plus 1, then the previous one will be fn, right? So the previous one is 3 we have here plus 3 here. So the previous one was 2 multiplied 3 plus 3 is 9. Then for 2, we go for the previous one, 9, right? For 3, we go for the value of this one. For 4, we go for the value of this one. So this is called as recursive. Here, another example, give a recursive definition of the factorial. So you know factorial, f0 is 1, fn plus 1 is n plus 1 multiply the previous one, the factorial of previous one. f5 is equal to 5 multiply f4, right? Or you can say 5 factorial is equal to 5 multiply 4 factorial. 4 factorial is equal to 4 multiply 3 factorial. 3 factorial is equal to 3 multiply 2 factorial. And so we want to give a recursive definition of this one, summation of ak, where k is from 0 to n. So the first part of the definition is ak is equal to a0. Then the second part is from 0 to this one is this part plus this one, right? an plus 1. Fibonacci numbers are very famous. This gentleman Fibonacci was Italian mathematician, and he found these numbers. He says that if f0 is 0, f1 is 1, then fn is summation of two previous one, fn minus 1, fn minus 2. So if you want to find out f2, then you should go for this one plus this one. If you want to go for f3, you need to find this one and this one. 4, you need to go for f3 and f2. For 5, you need to go for f5 and f. This is called as recursive functions. So far, we studied recursive functions, and absolutely we have recursive algorithms as well. I think in our lecture already we learned about recursive algorithms. Just to remind you, we call an algorithm as recursive if it tries to solve a problem by reducing it into an instant of the same problem but smaller input. These algorithms, instead of to consider the whole input as once, they try to use the same algorithm but smaller size of input. Then they try to solve it recursively. And there must be some termination. The instance of the problem must eventually be reduced to some initial case which is known. So here we want to find a recursive algorithm for factorial. I think you already know this one. Just simply, if it's 1 or 0, it will return 1. Otherwise, we try to find the factorial of n minus 1. You can see we send n minus 1 to the algorithm. We call this one as recursive. The algorithm is calling itself. Then come to here up to where is the termination? Here is the termination. You start from 5, come to 4, come to 3, come to 2, come to 1. 1 is termination, right? So in this way, we can find out factorial of n in a recursive mode. Another example, we want to have a recursive algorithm for computing a to the n, and a is non-zero and n is non-negative. We use recursive definition of a to the n, right? So what we have here, we receive in this algorithm, or this you can call pseudocode or function or anything, we receive two arguments. One is a and another one is n, right? We first check if n is equal to 0, then we return 1. We can say this one is our termination condition. Otherwise, this algorithm will run forever. So once it's here, we'll stop. But if not, we will go and call this function again. Why? We go for half of n. This time, we send half of n. And then we find x power of x. And if mode of n and 2 is 1, then we say x is equal to x multiply I, and we return. This is how we can go for exponentiation algorithm in a recursive mode. Also, we can find GCD in a recursive mode, greatest common divisor of two non-negative like a and b, and a is less than b. So, you remember that we say GCD of a and b is equal to GCD of b and a mod b. And we have the condition that GCD of 0 and b is b if b is greater than 0. So, very simple. Again, here we have termination condition. Then, if it's not 0, then we go for GCD of b and a mod b. As you can see here, GCD of b and a mod b. We repeat this one. This is recursively, and we finally find the GCD. You already know binary search algorithm. We want to have a recursive version. In summary, this binary search algorithm takes advantage of a collection of elements that already sorted, and we want to try to search something, right? So what we do, we make it half, and we compare what we are going to look with the middle one. If it matches with the middle one, it means we find it. Otherwise, if what we are going to find is greater than the mid element, then x can only lie in the right. It means greater half subarray after the mid element. Then we apply the algorithm again for the right half. Otherwise, if what we want is less than mid element, it means the target x is in the lower half, and we apply our algorithm to the lowest one. Very simple. Here we have binary search. First, in here, we check for the base if high greater than or equal to low. Then we go for mid is high plus low. This is floor division. If AR is okay, it means we found it, right? You can say this is termination. If it's satisfied, it means stop. Otherwise, if the element is smaller, if what we are going to is smaller than mid, then we apply the algorithm to the half. Otherwise, we apply to the another half, right? This is recursive. So we recursively make it smaller and smaller and smaller till we find it. In this way, we can do binary search in recursive manner. Merge sort is another algorithm that can be done in a recursive mode. So what we do in merge sort, it works by iteratively splitting a list when we have an even number of elements into two sublists of equal length until each sublist has only one element. Then each sublist is represented by a balanced binary tree. At each step, a pair of sublists is successively merged into a list with elements in increasing order. Then the process ends when all the sublists have been merged. The succession of merged list is represented by a binary tree. For example, I want to sort this list in ascending order. It means one should be first. What I do, how many numbers I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? I divide them. So first 5 this side, second 5 this side. This is 1, this is. Then again, I will apply 5 I have here, 3 this way, because I cannot divide to 2.5, right? So I have to select 3 one side, 2 one side, 1 and 1. Then again 2 here and 1 here. So finally we will have only 1. Then this one also 1. The same we will do here. Okay, now I will sort them in an increasing or ascending order. So 8 and 2, which one is smallest? So I will exchange them 2 by 8. Then here, 2, 8, 4, it should be like this, right? Then 6 and 9 is okay. Then I compare these two like this. 7 and 10, 7 and 10 and 1, 5 and 3 and 0. Then you can find. This is called as merge list. Two ways. One we go like this and one we go like this. First, we split the list in a tree. Then we try to sort them one by one. And here is function or algorithm. What we have a list, right? If n is greater than 1, then we divide by 2, stop floor. Then we have one part and another part. And then we merge sort, right? 2 times we call our algorithm, right? It's also even you have 2 lists, right? We want to merge 2 lists in order. If this is one list and another this list, right? So here we have 3 columns. First list, second list, we have a column merge list and comparison. First of all, I compare the first element of first and the first element of the second list. So 1 is less than 2, then I move 1 here. Then in here 1 is removed, we have only 4 and 2 is still there. I compare 2 and 4 here and 2 will come here. So 2 will be removed, 3 and 4. Then I compare 3 and 4. So 3 will move here and 3 will be removed. 5 and 4, 4 is less, 4 will be removed. Then 5 will come, then 6 will come. This is how we can do merging 2 lists in an increasing. Okay, this was the lecture on inductive and recursive. Very simple lecture. I hope you understand, and please feel free to ask me if you have any questions. Thank you.